Hi, my name is Scott Gaudi. I'm going to be talking about disks, exoplanet characterization, and exoplanet demographics with the Roman Space Telescope. So in case you're not familiar, the Roman Space Telescope was once called the Wide Field Infrared Survey Telescope, WFIRST. It was renamed relatively recently after Nancy Grace Roman, who was the first female executive in NASA, the chief scientist for several decades, and is often called the mother of Hubble. And you can see a picture of her right here. As I said, I'm going to be talking about both disks, exoplanet characterization, and exoplanet demographics. I'm not an expert in direct imaging of disks or exoplanets, so I borrowed very heavily from presentations by Ewan Douglas, Bertrand Menison, and Vanessa Bailey. Since I'm not an expert, everything I got right, you can attribute to them. Everything I got wrong, you can blame me. I'm also going to be talking about exoplanet demographics. There I know a little bit more about what I'm talking about, but I do have to acknowledge substantial input from David Bennett, Matthew Penny, and Samson Johnson, and the rest of the Roman Galactic Exoplanet Survey Science Investigation team. Okay, so just as a background, the Roman Space Telescope, one's called the WFIRST, was the #1 space recommendation of the 2010 Decadal Survey. Large space recommendation 2010 Decadal Survey. It was based on a number of mission concepts that were submitted to the 2010 Decadal Survey, including dark energy mission JDAM Omega, a microlensing exoplanet survey MPF, and then a near infrared all sky survey mission concept. And so it was prioritized again by 2010 Decadal Survey as the #1 large space mission recommendation. It currently has 2 instruments, or it will have 2 instruments, the wide field instrument, which is the main wide field survey instrument. It can perform imaging and spectroscopy over thousands of square degrees. It will monitor supernova and microlensing fields synoptically. Its wavelength bandpass is roughly between 0.5 and 2 microns. I'll show a little bit more specific information about the filters later. Each field of view is 0.281 square degrees, so that doesn't seem like a lot based on ground-based standards, but compared to HST, it's about 100 times the ACS field of view. There are 14 H4RG detectors that make up the focal plane. That's about 288 megapixels. And there are 7 image filters for imaging, GRISM, and PRISM spectroscopy. The Coronagraph instrument was added when the Roman Space Telescope was the 2.4 meter, which was donated to NASA, was chosen as the telescope for WFIRST. The larger aperture meant that it was feasible to do coronography. And so there's a Coronagraph instrument. This is a technology demonstration instrument. It is visible direct imaging from 545 to 865 nanometers. It can do polarimetry and spectroscopy, and it uses 3 different kinds of Coronagraph masks. In terms of the observations, the 2010 Decadal Survey prioritized 3 core surveys. One is a high latitude wide area survey to do, for example, weak lensing and redshift space distortions, a high latitude time domain survey to look for supernova, type 1a, and then a galactic bulge time domain survey to do exoplanet demographics using the microlensing technique. There's also roughly going to be 25% of the time or greater that will be devoted to general astrophysics surveys, and 3 months of chronographic observations during the first 18 months of the mission, and then perhaps additional observations with the CGI later. Okay, so I'm going to first talk about the prospects for imaging, directly imaging disks and exoplanets, mature exoplanets and young exoplanets with the CGI instrument. Here I'm not going to actually go into the science motivations behind this, or because I think that's been covered already in this meeting quite extensively. And I'm not going to go into the real technical nitty-gritty of the CGI instrument. I'm mainly just going to focus on what the capabilities are with regards to these particular science goals. So just briefly, this is a sort of a CAD drawing of the CGI instrument. Again, this is a technology demonstration instrument. It's not actually built to do science, although it is quite promising and will hopefully do a significant amount of interesting science, as I'll talk about. It's notable that it's the first space-based coronagraph with active wavefront control. There have been space-based coronagraphs before, but they've all been passive coronagraphs. And of course, we've had active wave control for ground-based coronography as well. But this is the first time this will be been done in space. Again, it's a visible light, so 545 to 865 nanometers. Also has a polarimeter and a R of roughly 50 spectrograph. In terms of the contrast, it will be a factor of 100 to 1,000 times improvement in performance over current ground and space-based facilities, as I'll show here in a minute. And as a result of this, it will be capable of exoplanetary system science and disk science as well. So this shows the sort of contrast limit, or the flux ratio of a source that you can detect, a point source, relative to the host star flux as a function of the separation from the host star. And you see here curves for both ground and current ground and space-based instruments, as well as future instruments like JWST. And you can see here the contrast range from sort of 10 to the minus 5 at the closest separations of sort of 0.2 arc seconds out to 10 to the minus 8, but these are very large separations where the glare of the star is relatively minimal. These squares show known self-luminous directly imaged planets. You can see here the flux ratios are 10 to the minus 4 to 10 to the minus 6, relatively large compared to a mature giant planet in reflected light. And so these are all easily detectable, or relatively easily detectable, using ground and space-based facilities. But if you look down here, these are predicted flux ratios for mature known Jupiters that are mature in reflected light. You can see here the flux ratios range from 10 to the minus 8 down to a few times 10 to the minus 10. Jupiter has a flux ratio relative to the sun of roughly a few times 10 to the minus 8. And if it's at 10 parsecs, then it has a separation of about 0.5 arc seconds. So you can see that that these flux ratios are considerably lower than what can be detected from the ground or current space-based facilities. Now this shows the contrast curves predicted for the CGI, both in imaging and spectroscopy. So here is the imaging in blue curve. This is for the hybrid Leo coronagraph mask, and this is for the shaped pupil mask in imaging in red here. And then this is spectroscopy with the shaped pupil mask. And you can see that, and then these diamonds here are actually the predicted visible flux ratio for the known directly imaged young planets connected by the dotted line. So the flux ratios in the visible are down by factors of a few hundred to 1,000, because of course these are self-luminous young, relatively hot planets, and therefore putting out most of their light in thermal infrared. But nevertheless, these are all well above the predicted contrast curves for the CGI instrument, and so should be readily detectable using the CGI instruments. And indeed, it will be possible to perform spectroscopy on these particular known planets, which will complement very well the spectroscopy that's possible using ground-based instruments in the near infrared like GPI or SPHERE. And you can see that for the known hot Jupiters, their predicted reflected light signature for some of them is just above these contrast curves. So it should be possible to detect and take spectra of a handful of mature giant planets around nearby stars. These are known giant planets. And of course, this is an image that shows a simulation of the dark hole that's created using the Coronagraph instrument with the active wavefront control. This just shows the primary imaging modes with the CGI, and spectroscopy modes with the CGI in the center of the wavelength. So the bandwidths are typically 10% to 15%, and you can see the 4 different channels here, ranging from 575 nanometers to 825 nanometers. And these have either imaging, narrow imaging, wide imaging or slit spectroscopy of R of roughly 50, and shows the sort of field of view of a radius, the coverage in terms of azimuth. So the hybrid LEO has basically 360 degrees coverage, whereas the shaped pupil has these sort of partial annuli on either side that span roughly 65 degrees. And so that shows the sort of field of view that you can do the spectroscopy. Okay, and there will be other filters and masks that will be installed, but not fully ground tested, and therefore will not be guaranteed to function at their highest level. Okay, so here's some science cases. First, as I mentioned, young self-luminous planets that are already known from ground-based direct imaging surveys will be detectable in the optical using the CGI, which is not possible currently from the ground because of the difficulty of doing adaptive optics in the optical. And so with this, we'll be able to get spectroscopy here at wavelengths between 0.5 roughly and 0.8 microns, which will allow one to detect spectral features that are relatively unique to the optical. So the CGI can then fill out the SED with broadband photometry and spectroscopy. And the CGI will have a technology demonstration phase. This is the initial 3 months of observations. And so during that phase, it will do this for roughly 1 to 2 systems. And then beyond this technology demonstration phase in sort of a GES observer science, it could do additional band passes or survey more known young self-luminous planets. And with this, we can answer such questions as, what are the cloud properties of these young massive planets? How inflated are they, and are they metal rich? It'll also be possible, as I mentioned, to get the first reflected light images of mature Jupiter analogs, at least for a handful of systems. So with this, you can see here's some simulated spectra of a Jupiter sized planet with solar metallicity, or 4.5 times solar metallicity, which is roughly Jupiter's solar metallicity, 30 times solar metallicity, which is about 6.6 times Jupiter's metallicity, and then a cloud-free Jupiter-like model. And those shown in the curves, you can see the spectra are very different. And so by getting some even relatively low resolution spectra of these objects, we can start to distinguish between these models. And this just shows simulated observation. So this is basically a single narrowband imaging detection. And then these are the R of roughly 50 spectroscopy that is possible. So this will be done for 1 to 2 systems during the technology demonstration phase. And then it'll be possible to do additional band passes or more planets in an extended guest observer phase of observations. And so this kind of shows how you can sort of fill in the spectroscopy with additional time beyond the technology demonstration phase that really allows you to characterize these spectra better and start to distinguish between some of these other models as well. And so that would be quite powerful. And this just shows a simulated image of a warm Jupiter at 2 AU from a star at roughly 3 parsecs. And you can see that this Jupiter shows up actually quite nicely. Okay, now I'll just switch to debris disks and exozodi disks. These are contrast curves are for point sources, but this shows roughly the flux ratio of a 15 Zodi disk around a star at 10 parsecs. And you can see that it just skirts above these contrast curves for imaging and spectroscopy using the hybrid LEO coronagraph and the shape pupil coronagraph. So we'd be able to detect relatively massive exozodiacal disks using the CGI. And also we'll be able to get polarimetry. The CGI has a polarimetric mode, and so be able to get polarimetry with the CGI. So some of the questions that can be addressed with this is, where does circumstellar material come from? How is it transported? What is the composition of dust in the inner regions of debris disks? So the CGI can map the morphology and the degree of polarization. And during the technology demonstration phase, it will do this for 2 to 3 known debris disks. And then beyond that, it could do this for additional disks with a variety of properties. And debris disks, as we've heard already this week, show a very, very large diversity of morphologies. And so the CGI will be important for being able to study those known disks in more detail. Okay, and in terms of the exozodiacal dust, so it's important to, the main science question here is how bright is the exozodiacal scattered dust and scattered light. And this is interesting not only because, as we've heard, this tells us something about the properties of the larger objects that are being collisionally ground down into dust in the system, and therefore it tells us something about the architecture of exoplanetary systems. It's also important because it is thought that exozodiacal light might serve as a significant noise source for direct imaging searches for Earth analogs around sun-like stars. And at the moment, our limits on exozodies are relatively weak based on studies of the Large Binocular Telescope interferometer. And so we'd like, if possible, to be able to get stronger constraints on specific stars that might be targeted for direct imaging surveys. And CGI, as I showed, can address this at the sort of the 20 exozodi level, which is roughly where it starts to become less important for direct imaging surveys. CGI can probe low density disks in the habitable zone of nearby stars, again complementing the LBTI Minute IR survey. And so this will be done sort of as a byproduct of the exoplanet observations and during the technology demonstration phase. And then beyond the technology demonstration phase, you could imagine a survey that targets the sort of best targets for future direct imaging surveys for Earth analogs and tries to characterize the specific amount of dust, exozodiacal dust, in those particular systems. And that, of course, would inform target selection for these future direct imaging surveys and the observation strategy. Okay, so now I'll switch gears and talk about what we can learn about exoplanet demographics with Roman. So just as a sort of motivation for why we want to understand exoplanet demographics, this is the classic plot that we always show in exoplanet demographic talks. Shows planet and planet mass as a function of orbital period, and planet radius as a function of orbital period for the known exoplanets. And they're color-coded by the method that was used to detect the planets. And you can see all sorts of interesting features here, some of which are real, some of which are selection effects. And you can see that different techniques are sensitive to different kinds of planets. But one of the most notable things about this figure is that analogs to essentially all of the planets in our solar system, except for Jupiter, would be essentially invisible from with any of the major detection techniques that have been used to find exoplanets. So we don't know how common solar system analogs are around other planetary systems. And so we'd like to be able to complete the statistical census that was begun by Kepler. And the way we're going to do that is using the microlensing technique. So microlensing works basically if you look at a star in the center of the galaxy long enough, another star will happen to pass very close to your line of sight to that background star, but very close, being about a milliarc second. When that happens, the foreground star's gravity will bend the light from the background star and split it into two images. Those images are separated by about a milliarc second, and therefore are not resolved, but the images, the star is actually magnified. So as the foreground star comes into close alignment, the background star is magnified, and then when it gets to the closest alignment is the peak magnification, and then the magnification falls off. And so you get this it's time symmetric magnification curve. Now, if the foreground star happens to have a planet, and that planet has a separation close to one of these images, that planet will further perturb the light from those images, and you'll create an extra little deviation on top of your planet. And so this animation kind of shows a foreground star coming into alignment with the background star. This foreground star has a planet, and so you see the background star getting brighter, and then when the planet intercepts one of the images, you can see that background star get a little bit brighter for a shorter period of time. And that's how we find planets with microlensing. So microlensing has a unique sensitivity compared to other detection techniques, which is why it's useful for completing the statistical census begun by Kepler. So it's sensitive to planets beyond the snow line. That's because that's the separation from the host star, the foreground star, that those images pass. It's about sort of 5 AU for a solar type star, 3 AU for a mid M dwarf. And that turns out to be roughly twice or 1.5 times the predicted location of the snow line for a protoplanetary disk. So that means you're sensitive to giant planets in the part of the planetary systems where we think they form. And in general, you're sensitive to cool planets, and you therefore are very complementary to the radial velocity and transit techniques. Now, microlensing is also very sensitive to very low mass planets, in principle, all the way down to roughly 10% the mass of Mars or a few times the mass of the moon. So you can get a very, very complete picture of the demographics of cold exoplanets. You're sensitive to long period and free-floating planets from separations from about half an AU all the way out to infinity, because planets without a host star act as microlenses just like the host stars do. So you can detect planets that way. Now you can, any star or remnant that happens to pass along our line of sight can create a microlensing event. And so you can look for planets around any of those kinds of objects. So you're sensitive to a wide range of host masses, from brown dwarfs to stars with mass less than the sun, and even remnants. The typical mass is roughly half the solar mass. And again, you don't need light from the source, the lens, or the planet. So you're sensitive to planets throughout the galaxy, and you can in principle measure the galactocentric distribution of exoplanetary systems and ask questions like, are planets less common in the galactic bulge than they are in the galactic disk? So Kepler provided the first large-scale demographic survey, as I mentioned, but was largely blind to planets with periods less than a year, at least for small planets. And so a complete ground census complementing that of Kepler would provide the ground truth needed to understand planet formation and evolution, and to test planet formation synthesis models, such as we've heard about this week. And in particular, the outer parts of planetary systems are important because, as I mentioned, we still think that most giant planets likely form beyond the snow line. We can use this to place our solar system in context, ask how common solar system analogs are. We think that most of the water for habitable planets likely was delivered from beyond the snow line. And as I mentioned, since we can probe the frequency of planets in the disk and the bulge, we can understand how the frequency of planet formation differs in different environments. Now, in order to realize microlensing's potential, you have to monitor of order hundreds of millions of bulge stars continuously. Hundreds of millions because the probability of any given star being lensed at any given time is roughly 1 in a million. So if you want a large sample of microlensing events, you have to monitor 100 million stars continuously. Planetary perturbations can last from an hour to a few days. So you really want to sample those microlensing events on a timescale of 10 minutes because the planetary perturbations cannot be predicted in advance. And that'll allow you to get very good characterization of these planetary perturbations, which is important because they can't be reobserved. The deviations, however, are actually relatively large. They're not the very small deviations we've come to expect from Kepler of 10 to the -4 for an Earth around a sun-like star. These deviations are a few percent, even up to tens of percent. And so you don't need exquisite photometry, you just need good photometry. And this photometry only needs to be relative, it doesn't need to be absolute. Now, if you really want to get the smallest planets, you have to monitor the smallest sources, because if the source is too large, the planet only magnifies a small part of the source, and the perturbation is both, the duration of the perturbation increases, but more importantly, the amplitude decreases and becomes very difficult to detect. So if you want to detect Earth mass planets and below, you have to monitor main sequence stars. And that means that you really need high resolution, as I'll mention. And the high resolution also allows you to resolve unrelated stars, which means that you can actually measure the flux from the host star lens. And that allows you to estimate the mass combined with some additional information, the mass of the star and the mass of the planet. So all of this actually drives you to space. And this was shown quite for the first time quite clearly in Bennett and Reed 2002. And you want to go to the space for several reasons. One is it allows you to go to the infrared, where you can look at more extincted fields, which allows you to get a higher event rate. And you can also look at smaller sources because they're more luminous in the near infrared, relative to the optical. Space also allows you to get high resolution, and so that means you can detect low magnification events on main sequence source stars and isolate light from the lens star, as I mentioned. And this is shown here in this figure made by Matthew Penny, which shows a simulated scene towards the bulge as seen by Roman. And this is a blow up of that, and the same scene as simulated for a ground-based image. And what you can see is clearly you see many more sources in the space-based image simulation. But more importantly, these individual objects that you might think are single sources in the ground-based image often turns out to be asterisms of multiple stars. And so that means that you're going to have more issues with systematic errors in the photometry, but more importantly, you're just not going to get the signal to noise that you would get for the space-based image where you're resolving out the light from the unrelated stars and from the background. And so that's one of the power of going to space. And you can see that by and large, all of the stars are resolved, at least for relatively bright magnitudes from space. The other thing that space buys you is you can get complete coverage, at least when the bulge is in the field of regard. So that allows you to get continuous coverage and catch all the planetary perturbations. And in space, generally, relative photometry has smaller systematics that allows you to characterize the planetary perturbations better and gives you the ability to robustly quantify your sensitivity of your survey. So all of this enables new science that can't be done from the ground. So this includes sub-Earth mass planets, habitable zone planets, free-floating Earth mass planets, satellites of planets, large moons of planets, and mass measurements for a majority of the planetary perturbations that are detected. Okay, so the tool we're going to use to do this is the Roman wide field instrument. So this just shows a CAD drawing of the wide field instrument. It's very big, roughly 1.7 by 1 meters. And this shows here the filters of the WFI, ranging from something sort of the bluest filter, which has a central wavelength of roughly 0.55 microns, out to a sort of K short filter, which has a central wavelength of sort of 1.84 microns. And that also shows the bandpass of the wide filter that is going to be used for the microlensing survey, which goes from roughly 1 microns out to 2 microns here. That's the W146 filter. It also shows the bandpass for the prism and the GRISM filters as well. This shows the field of view. Again, this is roughly 100 times Hubble, which is shown here in this little square. And so you can survey large swaths of the sky relatively quickly, or smaller swaths of the sky at a relatively high cadence. And this just shows 18 detectors in a engineering test unit, just to show that we actually, right now, the project has 26 science grade detectors, which will down select 18 of those for the final instrument. Okay, so what can we expect to detect with the bulge variability survey in terms of planets detected by microlensing? So this is a simulation done by Matthew Penny, where he simulates an area towards the galactic center, an area that's as close to the galactic center as possible, but avoiding very high extinction regions. This is an extinction map. These are so the nominal 7 fields in the survey he simulated, a total of 2 square degrees, again monitored in the wide filter at 15-minute cadence, and that gives you about 50-second exposures with the current estimate of the slew and settle time. There'll also be observations every 6 hours and alternating blue-red filters. We haven't completely decided what those are, but it'll be probably something like a Z filter and the KS filter or something like that. There's the bulge can be observed for about 72 days at a time with Roman, and so the nominal survey is 6 72-day seasons, which amounts to 41,000 exposures in the wide filter, and a total of 432 days of observation spread over the 5-year mission. I want to emphasize that this is a notional survey design. The final design of the major course community surveys won't be finalized until much closer to launch, and will only be finalized with extensive input from the community. So this should be thought of as a sort of notional survey that could meet the science requirements for the microlensing survey, but not necessarily what will actually be executed. Okay, so Matthew simulates a field of view with stars according to a luminosity function based on a galactic model, Besseson model. He injects microlensing events into those images, those simulated images, and then recovers the photometry. He injects planetary perturbations and then recovers those that are significant. This shows an example of a highly significant detection of a planetary companion that is roughly twice the mass of the moon. So this just shows the light curve itself. Again, this is a 27 sigma detection. So this is not a marginal signal to noise of 8 detection that we would, which is sort of the limiting sensitivity of Kepler. This is a very high significant detection. And in general, microlensing has a very broad range of detection significance of the perturbations. So they're not all piled up at the detection limit like they are with the transit surveys, for example. And so that means that these perturbations are unambiguous and can be well characterized, which is important because you can't go back and reobserve these again. As I mentioned, you can also detect free-floating planets with Roman and the Roman bulge variability survey. This just shows some simulated free-floating planet detections. So this is a free-floating brown dwarf, not planet. This is a 2 Jupiter mass planet, a 0.6 Earth mass planet, and then a Mars mass planet here. And again, you can see all of these deviations are quite significant and easily detectable. Also notice this very unique morphology. When you have a large source at a small planet, you get something that looks like an inverse transit. And this is based on simulations done by Samson Johnson, and that paper is available now. And he's currently working on a paper that talks about the properties, the parameters that you can extract from these free-floating planet events. This is the predicted yield. Of course, this depends on how common free-floating planets are, which is something we just don't know. So if you assume 1 per star, you expect sort of order 90 free-floating Earth mass planet detections, and about 18 free-floating Mars mass planet detections. If you assume something that's a log uniform in terms of number of planets per dex, you get these numbers here, which are slightly lower. Now, microlensing is not intrinsically very sensitive to planets, Earth mass planets in the habitable zone. That's because the habitable zone is generally located at a very relatively small fraction of the Einstein ring radius, which is where the detection sensitivity is peaks. And so planets that in the habitable zone tend to perturb images that are highly demagnified, and thus the perturbations are relatively weak. Nevertheless, there is sun sensitivity to potentially habitable planets. And so this plot shows simulations of planets as a function of their solar equivalent semi-major axis. So just 1 AU scaled by the square root of the luminosity of the star, and the planet mass and Earth masses. And the large filled circles are planets that were detected in the simulation around stars with mass greater than half a solar mass. And so when it comes to potentially habitable planets, microlensing is more sensitive to planets orbiting larger mass stars, which is good. And so, but the yields are not great. So you can see here, this is the habitable zone as adopted by the Habex and Louvois studies here in this gray shaded region. And you can see there's only a handful of detections. But for planets that are in the habitable zone but more massive, or planets that are just exterior to the habitable zone, there are more detections. And so you can imagine extrapolating from these planet detections into the habitable zone. And this is actually very similar to the situation that we're in with Kepler, where Kepler only has a handful of potential candidates that are in the habitable zone of sun-like stars, and therefore has to extrapolate from interior to the habitable zone and planets larger but in the habitable zone into the habitable zone, this gray box itself. So Kepler does an extrapolation outward. Roman will do extrapolation inward. In principle, with a mass radius relationship, you can do an interpolation between Roman and Kepler into the habitable zone and get a better estimate of Eta Earth. This is work that is been done by Samson Johnson and is currently in preparation. Okay, so to summarize, by combining Kepler and Roman, you'll get sort of a complete statistical census of planetary systems in the galaxy. This plot shows the sensitivity of both Kepler and Roman, here previously W first, as a function of semi-major axis. The red line here is roughly the sensitivity limit of Kepler. The red dots are known Kepler detections. The black dots are known exoplanets from other methods. And this blue line is the sensitivity limit based on Matthew Penny's simulations for Roman. You can see that it peaks at sort of a few AU, 3 AU, and gets all the way down to a few times the mass of the moon. So this is the planets in our solar system. You can see that Roman will be sensitive to analogs of all the planets in our solar system except for Mercury. This is the moon, Ganymede, and Titan. So for Ganymede analogs, Roman will be able to detect a handful of them. And the blue dots are simulated planet detections. These are just completely made up. If we knew the answer to this, we wouldn't actually have to do the survey. This right bar shows the sort of predicted yield of free-floating planets. And you can see that there's sensitivity all the way down here to the planets with mass roughly that of Mars. So with this survey, we expect about 1,400 bound planet detections, some sensitivity to outer habitable zone planets, analogs to all the solar system planets except for Mercury, as I said, hundreds of free-floating planets, including a significant number with mass less than that of the Earth. We'll be able to characterize the majority of the host stars and therefore measure their masses and the masses of the planets. We'll get the galactic distribution of planets. We'll be sensitive to lunar mass satellites. As I'll mention, we'll also be able to detect about 100,000 transiting planets. So I'm going to finish off by talking a little bit about the statistical power of this galactic bulge variability survey, or the RGES survey in particular. So this shows the uncertainty, the photometric uncertainty, relative photometric uncertainty as a function of the wide band magnitude, W149 magnitude. And we've assumed a systematic floor of about 1 millimagnitude. And you can see that even all the way down to sort of W149 of 21st magnitude, we expect better than 1% relative photometry. And the total for a typical star of 21.15, we expect to get about 1 billion photons over the course of the survey. And we're going to get, as I mentioned, 41,000 images, which means that if you can, if you just based on statistical power, you can actually improve your single measurement precision by a factor of 200, either in the photometry or in the astrometry. So this shows the number of stars in the RGES survey as a function of this W149 magnitude. And you can see that it ranges from sort of 1 million stars all the way out to hundreds of millions of stars at the faint end. And we expect roughly 27,000 microlensing events with impact parameter less than 1 Einstein ring radius. So there's going to be a large number of microlensing events. And this shows rough estimates of what we expect for the photometric precision and astrometric precision, single measurement precision, as a function of the magnitude in H, AB, as we transform from the wide field magnitude to the H magnitude, and the number of stars for which we can achieve these precisions. So down to 21st HAB, we expect about 40 million stars with 1% photometric precision per exposure and about 1.5 milliarc second astrometric precision per exposure. Now, again, these are relative and Poisson noise only. They do not account for any systematic effects. It's obvious we have to characterize the detector exquisitely in order to be able to achieve these statistical precisions. But if we are able to do that, there's an enormous amount of auxiliary science that will come with the Roman or W1 survey. So first, we'll be able to measure the mass function of condensed objects over 10 orders of magnitude. So this is free-floating planets, brown dwarfs, stars, and stellar remnants. And we'll also be able to learn about the binarity of those objects as a function of the primary mass. We'll detect of order 100,000 warm and hot Jupiters and Neptunes via transits. We'll get astroseismology of about 1 million bulge giants, parallax and proper motions of about 6 million bulge and disk stars, detection of about 5,000 trans-Neptunian objects. We'll detect variable stars and much, much more. So I'm just going to highlight one particular science application that I mentioned. This is a transiting planet. So as I mentioned, Roman will detect 100,000 transiting planets. This is just simply because we know the frequency of hot and warm Jupiters and Neptunes from Kepler and ground-based surveys. They're of order of 1% or greater. The transit probabilities are order 1 to 10%, and we're looking at hundreds of millions of stars. And so that gives you about 100,000 transiting planets. This is the first shown by Bennett and Ree, where this is the paper that first advocated for a space-based microlensing survey. It was explored in much more detail by Ben Monte et al. in 2017. This figure is from that paper showing the number of detections as a function of the planet size and the host star spectral type. And you can see that the total number of planets is up to sort of 70,000 for solar type stars in the bulge. And of these, we expect dozens to be in the sort of 2 to 5 Earth mass range, up to hundreds for M companions. So we expect a very large number of transiting planet detections. Now, it'll be difficult to difficult or impossible to do radial velocity follow-up of these systems, not just because of the sheer number of them, but also because the target stars are so faint. Monte will explore a number of ways in which we can try to eliminate false positives using transit timing variations or secondary eclipse observations. But by and large, it'll have to be done statistically. And so exactly what we can learn from this sample of planets is not clear, and it should be something that should be explored in the future. Okay, so just to summarize, the Roman Coronagraph instrument is a technology demonstration instrument. It will be the first active coronagraph in space. It will be a pathfinder for future reflected light direct imaging missions that aim to characterize Earth analogs. So this is HabEx or LUVOIR as an example. It also will be capable of novel exoplanet and disk science. So it'll be able to image and take spectra of young planets in the optical. It'll take the first reflected light images and spectra of mature giant planets, and we'll be able to image and get polarimetry of circumstellar debris and exozodiacal disks. And important to recognize that that there will be a lot of community involvement in defining the coronagraph instrument, both the technology demonstration observations, but also any guest observer observations. And so encourage you to think about getting involved by the CGI Community Participation Program. In terms of demographics with Roman, as I argued, microlensing is complementary to other planet detection techniques and will allow us to complete the statistical census begun by Kepler, but realizing that full potential requires going to space. But by doing so, it will complete the census begun by Kepler, revolutionize our understanding of cold planets. It'll enable qualitatively new science that's not possible from the ground. So sub-Earth mass planets, free-floating planets, outer habitable zone planets, mass measurements, giant satellites. And because of the sheer number of observations, the quality of the observations, and the number of stars that are going to be monitored, there's an enormous amount of auxiliary science that can be done with the ARGES survey. And importantly, again, the final survey design is not set, and there will be broad input from the community. So I encourage you to think about this and get involved. Thank you.